All right. All right. So this is lecture 16. And today is the 12th of February 2021. Okay. So let's see where we are and where we are going as before. Okay. Well, very quick overview. See where we are in the course of statics. We started with forces and then discussed all the sort of characteristics and the knowledge about forces that you needed to know so that we can deal with them, including the translational effect, rotational effect, moment, and we came to understanding what is equilibrium of a particle. Then we moved to equivalent systems. And then the last topic, before we got into the centroid and moment of inertia, which was kind of a detour, we discussed was rigid body equilibrium, okay? And we said that the objective of studying rigid body equilibrium is twofold. One is how to find external reaction or support forces that keep the structure in place, the whole structure in place. Then we said the next step or the objective would be, okay, to find all internal forces. And what did we mean by that? That is, any structure is made of components. These components or pieces are connected together. I always gave you the example of your chair that has different pieces. They're all connected together. And we, in order to design a structure like that, we need to know how much force each joint will carry so that, for instance, we can use the proper welding or proper bolt to withstand those forces. Okay, so let me sort of basically quickly kind of give you an overview of what we did so far. Of course, we did discuss this, but instead of going directly to this topic, we took a detour, which was the centroid of moment of inertia. Now we are coming back to this, which is the heart of statics. So what we've done so far, or what we discussed so far, was what? We had a structure like this. We call that, say, frame, or whatever that was, that doesn't matter. But the objective, the function of this structure was to carry some loads, okay? And we said the objective for this was that to find these unknown reaction forces. So first of all, we showed you what these supports represent. If this was, say, a roller, represented a vertical load like this. This is a pin, represent these two unknown forces. But the procedure for the solution was that you set up an XY coordinate, okay? You draw the free body diagram of the whole structure, meaning you detach this structure from these supports and put the effect of these supports, which is what I did, okay? Then step 3 was use equations of equilibrium, and of course, preferably starting with summation of moments equal to 0, because that is the equation which always leads to one equation, one unknown. But anyway, that's what we've studied so far. So now what we are going to do, we're going to move to the next step, and that is Okay? Internal forces. How do we find internal forces in a structure? First of all, we are not going to look at all possible structures in the world. We would, first of all, sort of model these structures, or set up some kind of a symbolic modeling of these structures, and then we try to address that objective. The types of structures that we consider in statics are basically two. So the structures that we consider are two: frames and trusses. And the way we separate these are based on the inherent characteristics of each of these structures, okay? But in all of these, both of these, they're made of pieces that are connected together, okay? So, and these structures both made of pieces, and they can carry loads. That's the main function of any structure. Okay. I will always start with frames as the first type of structure that we study. And the reason for that is this is a general case, this is a special case. So I would start, in contrast to the book that starts with trusses, I always start with frames. So let's see what is a frame structure, or what characterizes a frame structure. A frame structure, okay, is a structure obviously made of several elements, components, pieces, whatever terminology you may use, connected together. Okay? Now, these members can be connected to one another at any point along each member. Why is this important? Because I want to emphasize that if you have a frame, every piece can be connected, versus you can bring another piece, just connect it in the middle of this, put a screw there and connect the two together. In trusses, that's a different case, okay? We'll talk about that. These connections can be, okay, pins or fixed. So you can bolt these pieces together, you can weld them together. Weld is a fixed connection, bolt is a pin connection. And then, so if I want to number these are the four main characteristics. Loads that act on the structure can be applied anywhere along a member. They don't have to act, for instance, only at the two ends of a member. So let me demonstrate this first qualitatively, okay? And then we'll talk about a quantitative approach, which is solving for these unknowns that we talked about, okay? And what are the objectives? Let's say this is a typical frame structure, okay? I will draw something. You have a piece, maybe a bar, okay? You take another piece which looks like this. You drill a hole here on both and bolt them together, okay? Then you're basically building a structure that is supposed to support some external load that is acting on the structure through this pulley, and then maybe some other additional external load somewhere else, okay? So this is a typical frame structure, okay? So let's review those elements or the pieces that I mentioned about. I said, made of several components that are connected together. You look at here, this piece, this piece, this piece, this piece, right? And this piece. They're connected together at different points along each member. These connections, okay, can be at any point. You see, for instance, this member is connected to the middle of this member. This member, which is the pulley, is connected to the end of this member. This member is connected to the end of this member and the middle of that member. And this member is only connected at its two ends to the rest of the structure, okay? And I said, connections are pinned or fixed. You can see that all the connections in this particular frame are all pin connections. And then the last characteristic was that loads can be applied anywhere. You have this load acting at the end, you have this load along the member, these loads, and of course, obviously, due to these connections, there's a load coming to this member from this member, and so on. So this is a typical frame structure, okay? So what is the objective of analyzing a structure like that? The objective is twofold. One, okay, is find external support or reaction forces, okay, which you've already done this. If I gave you a structure like this with all these loads acting on that, what did you do? You took the free body diagram of this, and following the procedure I mentioned, you could solve that. But the second objective, which is what you are going to address, okay, is this: find all internal forces. What do we mean by that? See, if I label this, let's say A, B, C, D, E, F, G, H. What I want to do is I want to take all these pieces apart, find out what is the force that is holding these two pieces together. What is the force at C that is holding these together? What is the force at G? What is the force at D, E, F? That's the part that we have not done, okay? And we want to do, okay? Any questions so far? No? All right. Before I go any step further, okay, I want to emphasize on a very important concept, and then I will talk about the procedure for performing this operation. What is an important concept? An important concept that understanding of it is detrimental, is critical, is a key to solving frame problems is a concept called two-force members. And what is that? Okay. In many frames, you may end up with a member that has these three properties or characteristics. I will first tell you what those are, and then I will tell you why then it is important to detect a member like that in a frame structure. A two-force member is a member with these three inherent characteristics. Number one, it is only connected to other pieces at the two ends. Number two, all these three characteristics should be satisfied for that member to be a two-force member. Okay? All right. Number two, these end connections, okay, are pins. Number three, okay, no load acts along that member. Okay? So all these three conditions should be satisfied. And if these three conditions are satisfied, we call that it is a two-force member. Do you see a two-force member in this structure? Let's look closely. This has connection at the two ends, but also another member is connecting to it. And also, not only that, there's another load coming here. Same thing here, same thing here, same thing with this. But you look at this member and you say, wait a minute, this member is only connected at the two ends to the rest of the structure. These two ends are pins, and there is no load in contrast to all the others acting on the structure. So this is a two-force member. So what happens if you have a two-force member? Let's say you have a two-force member of any shape, right? Doesn't matter what the shape is. As long as it is only connected at the two ends, these two are pins, and no load acts along this member. This is a pin, and this is a pin. So you have basically an unknown force here, an unknown force here, which you typically broke them down for the analysis into their two components, right? So let's call this F1 and F2. And you say for this member to be in equilibrium, those are the two forces, right? So now let me connect the two ends along this line AB. So to solve for these unknowns, what I will do, I will resolve this force and this to its components, and this force into its components. So I'm going to call this F2y, F2x, F1y, F1x. All right? In other words, this is x, y. So I want to solve for these unknowns. What do? I will take summation of moments about A is equal to 0. If I do that, what happens? This force goes through A, so I have only this one. So if this vertical distance is D, this equation leads to F1y times D is equal to 0, which means F1y has to be 0, right? So if F1y is 0, I write the other equation of equilibrium, which is summation of y. Force along y equal to 0. and I have F1y plus F2y is equal to 0. Since this is 0, F2y has to be 0 also. So these two cannot exist if this is going to be in equilibrium. And I can have only two forces acting along x. But wait a minute. If I write summation of force along x equal to 0, you can easily see that then F1x has to be equal to F2x. This is not just a conclusion, but the property, the inherent characteristics of a two-force member that we have proven. And what did I do? I proved if you have a member that satisfies these conditions, what happens? For that member, for a two-force member to be in equilibrium, okay, forces acting at the two ends, one must act only along a line connecting two ends, right? We proved that we cannot have force acting in any other directions. They have to be acting along this line. And two, these forces are equal and in opposite direction. So that means if I take this member apart, this member EG, the only way this member can be in equilibrium is that if you draw a line like this, you have only a force acting this way, in this direction along this line, and that one here, and these two forces are the same. This is the concept of two-force members. Any questions before I move any further? If not, now that we've learned what a frame structure is and what is a two-force member, we are going to set up a procedure for solving frame problems, okay? And I want you to remember that. In other words, I emphasize again, okay? I emphasize again, statics is not about being able to set up a bunch of algebraic equations, which we call them equations of equilibrium, and solve them. The most important aspect that you need to remember, okay, is the procedure, the process. The process is the most important one. And what is the process or the procedure for solving frame problems? I want you to follow these. And if anything you remember from Professor Nouri is that he emphasized this concept of methodical approach to solving problems, okay? What is this method? Number one, if you're given a frame structure, you draw an XY set of axes. Let me remind you, by the way, that from now on, we are only going to focus on 2D problems. So we're not dealing with any longer with the 3D structures. We only have 2D structures. So you set up an XY axis. Number two, detect any two-force member, okay, in the frame. Number three, once you've done that, you draw the free body diagram of the entire structure as if you don't know anything about frame analysis. Just follow what you were doing before. That is, just separate, okay, the whole structure from its supports. Okay, that's it. Do not cut any internal piece. You may think this is redundant, what I'm saying, but let me tell you this. Like, we had a final exam problem, and one of the younger colleagues showed the free body diagram that he had asked his student to draw for a problem that included a pulley. And this was the kind of the problem, something like this. I don't remember that exactly, but you had the member like this, the pulley like that. It was holding something like this. Okay. And the students were asked to find the support reaction forces. And he had told them this is the free body diagram. Two unknowns here, one unknown here. Since there is a load of, say, 100 pounds here, you cut this here, so there is a load here and there's a load here. You don't do that for the frame whole structure. Do not touch anything inside, even if it's a pulley or a cable. Just draw the free body diagram as if this is just one piece and all you're cutting are the external supports, okay? So once you've done that, step number 4 is this. Draw free body diagram of each piece by taking all member after you take after taking okay, not by, sorry, but that after taking all members apart. Once you've done that, okay, remember third law of mechanics as you're taking these apart. What is that? If you have two pieces coming together, right? This member and that member, you want to draw the internal force at C acting on this member. Whatever that force is, whatever direction you assume for that force, when you draw the free body diagram of this piece, at that point C, you have the same force acting in the opposite direction on this member, okay? Once you've done that, you set up all the free body diagrams, then this is the essential part. You start by, okay, looking at all free body diagrams, okay, and consider the one with least number of unknowns, okay? Solve for as many of those unknowns as you can and move to the next free body diagram with least number of unknowns. Okay? Until you're done. However, good news, okay? If you've done this correctly, okay, you always end up with one free body diagram that is not used. Use that to verify your solutions. Okay? I want you to remember these and follow this procedure to save you headache, to save you from making mistakes, and make your life a whole lot easier in dealing with frame problems. So let me show what I have said here first, qualitatively, and then quantitatively. Okay? That's what I want to show. Okay? Let's say you have, or elaborate basically on this. The good thing is we are one day ahead of the schedule, so we have one extra day next week to solve more frame problems. So I'm going to show you through the example that I had set up qualitatively what I mean by, this procedure. Okay. So this is the problem we had, right? Okay. Let me label those. B at point C, let's say you have a 30 Newton force. This is point D. You have, let's say, this is member, okay, J, G. This is point M. Let me label that as E. This is the weight that this structure is carrying. You have a roller as the external connection here. So this is a structure. This is a frame structure. So let me show you the step-by-step. What did I say? Draw an XY coordinate. Okay? All right. We draw an XY. This is the XY coordinate, and it is important because we want to know, as we solve those equations of equilibrium, whether the answer comes out to be positive or negative, and so on and so forth, right? What we have discussed, okay? All right, okay? So this is the second step. Detect if you see any two force members in this structure. Do you see a two force member in this structure? Okay. Of course, we talked about that before. This member only connected at the two ends. The two ends are pinned. No load acts along this. Those criteria are not satisfied by any of these members, including this pulley. Okay. So detect two force member, in this case is member GJ. Okay. So now step 3, draw free body diagram. Let me remind you, draw the free body diagram of the structure. Okay. Free body diagram of the structure. Not the pieces, but what you had before. In other words, the structure, as far as you're concerned, it is this whole thing that is connected at these two ends. So just draw that free body diagram. This is a roller, RH. This is a pin, AX, AY, right? 4, draw the free body diagram of each piece, okay? And remember law of mechanics, third law of mechanics. So I had this 2-force member. Let me start with that guy. So free body diagram, let's say I assume forces Rj and Rg, which are of course equal, or acting like this. So this is free body diagram 1. Let's look at this member, A, B, M. At point B, you have a pin connection. That means there are 2 unknown forces, okay, that this pin represents, right? And remember, don't care about if these directions are right or wrong. After, as you've seen before, you solve for those unknowns. If they turn out to be negative, that means the assumed direction is wrong, okay? Same thing here, mx, my. Now I go to the next member, okay, which is B, C, D, J, and let me call this, let's say N. So what do I have here? At B, forces acting on that member were assumed to be in that direction. So I need to follow the third law of mechanics and put these unknown, which are the same unknowns, in the opposite directions. At D, I haven't considered the other member. So, okay, let's say this is dy and dx. How about at J? J, this is the key. You have only one unknown, Rj, not 2 unknowns. And that's why detecting 2 force members are important, because if these are 2 independent unknowns, you end up with more unknowns, as you will see the end number of equations that you have. So you cannot solve them. At N, you have a pulley. So I'm just assuming these are the directions. So that's the free body diagram of that member. What else? I have this member and the pulley. So let's start with the pulley. I have load of W on this end, which should be W on that end. And I assume this is upward, so this force should be assumed downward, and this is an X, because I assume that's the direction they're acting on that, right? I don't know if it's correct or not. We'll find out. This one, I have this force W at E, same force here. At D, I had assumed directions of the force on this member are here like this. So on this member should be equal, opposite in direction. How about at M? Again, at M, these were the directions I assumed for this connection on this member. So on this member should be the opposite, mx, my, okay? How about at this G? This is the assumed direction, so this would be the assumed direction here. And at H, this is RH. So I have 1, 2, 3, 4, 5, and 6 free body diagrams here. Okay? So what did we say? How do we go ahead, solve this problem? Start with number 5, right? Remember? Start by looking at the free body diagrams and select the one with the minimum number of unknowns. Let's do that. 3 here, 1, 2, 3, 4, oops, 5, 6 here, 1, 2, 3, 4, 6, 7 here, 1, 2, 1, 2, 3, 4, 5, 6, 7 here, 1, 2, okay, here, because these are given. So which one is the best free body diagram to start with? This has 2 and this has 2. Remember with the 2 force members that you cannot use that free body diagram to find that unknown, because you've already used the free body diagram and the equations of equilibrium for that member, which has led to the conclusion that you have these 2 forces equal in magnitude opposite in direction. If you write summation of forces along x or y equal to 0, all you get that this is equal to that. So you cannot use free body diagram of a 2 force member. So that's out. So of all the 5 more that you have left, this is the one with 2 unknowns, right? So I will start with number 5. Write equations of equilibrium. Summation of forces along x equal to 0 gives me negative w minus negative x is equal to 0. So nx comes out to be negative of w. That means the assumed direction for nx is wrong. As soon as I detect that, you remember, you have to make the correction, not only on that free body diagram, on all other free body diagram that this force appears, which is here. So I would have to make that correction. Then I use the second equation, and that will give me ny, negative ny minus w is equal to 0. That is, ny comes out to be also a negative value. That means this is wrong. The assumed direction is wrong. The correct direction is this, so I have to also correct this one. So I found 2 unknowns, okay? Now I move to the free body diagram with the least number of unknowns. So I'm done with this, I'm done with this. Let's look at all
I have
these
a
free
quick
body
question before you move on.
diagrams. Sure.
For your sum of y direction, it doesn't
Mhm.
look like the weight had like a y component. So why did you have that?
Oh, the weight was downward. You see, this is the weight.
That's that isn't that the
That is
n?
external. No, no, this is N. N is at the
What's
pin.
W on that drawing?
That's the weight. That is the weight, external force,
But it's
given. This is the given force.
okay.
Let's say this is 20 Newton.
Why do you
So
have
this,
2W's on that pulley?
because if you have a pulley, remember pulley from physics, regardless of they attach these cable that goes around the pulley, forces on the 2 sides are always equal, right?
Okay.
That's why. So if this is W, you're taking out this pulley out, right? So if this is W, this has to be also W. Does it answer your question?
Yeah, that does. Thank you.
Sure. So these 2 are out. Let's look at, of the 4 that are left, which free body diagram now I can go after. I have this given. So you have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. How about this guy? 1, 2, 3. So now I go to the free body diagram of the structure as a whole. Okay? The reason I didn't go with that one first, which you could, because you've already seen how to solve external forces, is that sometimes the structure may have a free body diagram that has more than 3 unknowns. So the general procedure that I strongly recommend you to follow is methodical approach. You start with the least number of unknowns. And as you saw, With this free body diagram, we have 2 in contrast with 3. Okay? So of course, we won't be able to solve this problem, but if once you solve these 3, now you have this one out of the picture, and this one. Then you look again. This has now 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3, 4, 5. So you have 2 free body diagram. No, I mean 1 free body diagram now has the least number of unknowns, and this one. So you go with that, solve for as many of those as you can, and then move to the next. And by doing that, you will be able to solve for all the unknowns, and you end up with 1 free body diagram that is not used. I cannot, of course, solve the problem today. I just wanted to present you the procedure. We will be doing a lot of problems next time and next time. And so you will become an expert in doing frame problems. Any questions before I leave? And as I said, I apologize again for